Welcome back, students. In this video, we're going to look at cycloalkanes and some of the most common conformations of the most commonly looked at cycloalkane, which is cyclohexane. Cycloalkanes are just alkanes that are cyclic. Cycloalkanes are going to have a certain number of carbons in them, and they have a ring structure. In this case, we're looking at things that are just alkanes, meaning there's no double bonds or triple bonds within the ring. And you might pause and think, triple bonds in a ring? You'll get to that at one point in organic chemistry too. So here's some examples of cycloalkanes, and these do not all have the same stability. There is a balance of stability for your cycloalkanes. And normally your textbook will go through and they'll look at cyclopropane first and they'll explain why it's not stable. And then they'll look at cyclobutane and they'll explain why it's not stable. Then they'll look at cyclopentane and show that it's more stable than the first two, but still not quite as stable as cyclohexane. In our case, I want to tell you about the types of strain that are leading to these instabilities and then focus solely on cyclohexane because that's where you need to spend most of your energy. The reason that cyclohexane is so stable is because it's minimizing these three types of strains. The other compounds, the other cycloalkanes that are not as stable, have one or more of these kinds of strains. Let's look first at angle strain. Angle strain is considering the bond angle of the actual molecule versus what the angle should be based upon hybridization. If we look at something like cyclopropane has a bond angle of 60 degrees, which is ridiculous, because this is an sp3 hybridized carbon and it should have a bond angle of 109.5. So what ends up happening is the orbitals of the carbon, the sp3 hybridized orbitals, in order for them to kind of minimize this angle strain, they bend outward and barely overlap, and thus cyclopropane is highly reactive because it has a much more stable energy state to get to if it reacts. So angle strain is looking at like the geometry that you would expect in geometry class, that these angles would be 60 degrees, and comparing that to what is the angle that you would expect with hybridization. And when those angles don't line up, that leads to angle strain. Another idea is called steric strain. Steric strain are when you have two groups on a molecule that get too close to one another and their electron clouds end up repelling. We're going to see an example of this later on. This would be something like if I have this boat conformation, which we'll look at later. If I have a group here we'll call X and a group here called Y, the electron clouds of these two groups are getting too close to one another and they're repelling, and that's what steric strain is. Our last type of strain is called torsional strain. Torsional strain was something that we saw in Newman projections. When you're looking at Newman projections, part of the reason the eclipsed version of the Newman projection is so unstable in comparison to the staggered is because when you have your Newman projection, these electrons that make up that carbon-hydrogen bond and these electrons that make up that carbon-hydrogen bond, and I'll just finish drawing the Newman projection to be a good chemist. So the two sets of electrons in the bonds that are highlighted, those are too close together. And electrons repel, and so these end up increasing the energy of the molecule because of that strain. So overall, what we're seeing is that cyclohexane ends up being in a conformation where all of these strains are reduced, and that's what makes it so special. Let's look at the most stable conformation of cyclohexane. When we're looking at this we will see something that is called a chair conformation. Why is it called a chair conformation? You know what? This is my hypothesis. My hypothesis is when you look at this conformation, which I've drawn off to the left without the hydrogens on it, to me it kind of looks like a chaise lounge, right? If you have your head up here and then your body is chasing this way. I'm not a great drawer. You have a tail, so that's staying. And then you got some hair, maybe your chemistry goggles. So it looks like a chair, I guess, to some chemists, the people who named it. And this chair conformation ends up minimizing all the strains that we saw previously. If we were to draw the Newman projection for the chair conformation, we would see that all of the atoms are staggered with respect to one another, so there's no torsional strain. The reason that you see this like bending situation is to make sure that the angles are really, really stinking close to 109.5, and so we don't have angle strain, and there's currently very little steric strain. So this is the conformation that is our go-to. Notice how we have two different colors of hydrogens. We have a set that's black and a set that's blue. So the set that's black, these are in what's called the axial positions. So these are your axial hydrogens. And see how there's an AX there? That AX is the abbreviation for axial. Then the other hydrogens that I will highlight in blue, these ones are your equatorial hydrogens. When I think about equatorial hydrogens, I think about the equator. If I am kind of picturing the Earth, you know, the equator runs around the middle, while your equatorial hydrogens are also running around the middle. I'm going to show you your first chair conformation. Here's a chair conformation where I'm holding on to an axial hydrogen, and all of these protons around the middle are your equatorials. And your axials are either pointing straight up or they're pointing straight down. So we want to get used to the fact that we have these two types of positions in our chair conformation. There's another conformation that's commonly talked about, and that is boat conformation. Now, cyclohexane does have numerous conformations. The usual ones that you'll see in textbooks are chair, boat, twist boat, but these are the two that we mainly talk about. Boat conformation experiences more strain than your chair conformation. And let's look at the two types of strains that the boat conformation is experiencing. So the first thing is boat conformation is experiencing steric strain. And when we look at these hydrogens that I'm highlighting in yellow, these hydrogens have small electron clouds. Yes, if they were bromines or something that had more electrons, they'd have bigger electron clouds, but there's still electron clouds for those hydrogens. And those hydrogens, they're just getting too close to one another. And when they end up getting too close to one another, that is what steric strain is. For your steric strain, this specific kind of steric strain is called flagpole interactions. And strain is not good. Strain increases the energy of the conformation, which makes it less stable. Your boat conformation also experiences torsional strain because what's happening in this boat conformation is you have a hydrogen here and a hydrogen here that are eclipsed to one another. Right? And it's the electrons in the bonds to those hydrogens that are eclipsing that are giving rise to that torsional strain. And notice how it's not just that pair of hydrogens, there's also other pairs of hydrogens that are eclipsing, and that's increasing the energy, which means the boat conformation is less stable. What will happen at room temperature is that the chair conformation will twist through a variety of other conformations and just be at equilibrium most often in the most stable conformation, which is chair, which is why we spend so much time talking about the chair conformation. Let's wrap up. In this video, we looked at what cycloalkanes are, and we considered that for cyclohexane, that the most common conformation and the most stable conformation is the chair conformation. The cyclohexane does come in a variety of conformations. The two that are most talked about are chair and boat conformations, so we looked at those a little bit more thoroughly. We also talked about the different types of strains that lead to an unstable conformation. And those types of strains are not very present in your chair conformation, which is why it takes up the majority of our discussion. In our next video, we're going to look more at chair conformations, so stick around.